Thanks for the introduction. Hello, everyone. My name is Dikta Rukmaji, and today I'll talk about a paper titled The Green Mirage, Impact of Location and Market-Based Carbon Intensity Estimation on Carbon Optimization Efficacy. So this is a joint work with Noman Bashir, David Irwin, Prashant Shenoy, and Ramesh Sitaraman at UMass Amherst. So in recent years, many consumers are trying to reduce the carbon emissions associated with their electricity consumption in order to mitigate climate change. The main paradigm for this emission reduction is this measure then optimize paradigm, where a consumer first measures its carbon intensity of electricity, which is the carbon equivalent emitted per unit of electricity consumed, and then they optimize their carbon emissions, which is a product of carbon intensity and the electricity consumption. So once carbon intensity is measured, and since it varies both spatially and temporally, consumers can shift their electricity consumption from high carbon regions or periods to low carbon regions or periods to lower their carbon emissions. However, measuring carbon intensity of electricity is not straightforward. So carbon intensity is basically the weighted average of the carbon emitted by each electricity generating source in a region or in a grid. And so it depends on how much green electricity is available in the grid and to whom that green electricity is attributed to. So for a consumer, the more the fraction of the attributed green energy in its consumed electricity, lower is the carbon intensity and hence lower the carbon emissions. But today, there are two methods to attribute green electricity. One is location-based and another is market-based. And so carbon intensity can be measured in multiple ways or two ways. So we'll look at both these methods now. So the first method, or the location-based method, says that once electricity has been delivered to the grid, we really cannot segregate the different sources that generate electricity. So assume that there's a toy grid with two sources, coal and wind, and each generate 50% of electricity. So the location-based method says that once they have been delivered to the grid, each unit of produced electricity will have 50% wind, that is 50% of green electricity. And so any consumer in this grid, for example, the house and the data center, they will receive 50% green electricity per unit of electricity they consume. And so the carbon intensity is basically the weighted average of carbon emitted by all the sources in this grid, which is coal and wind. And so if we assume that the carbon emission factor of coal is 1,000 and wind is 0 grams per kilowatt hour, so we're talking about scope 2 or operational emissions here, then the carbon intensity can be calculated using this formula, and it comes up 500 grams per kilowatt hour. And the weight's 0.5 because like each source is generating 50% of the electricity. And we call this CILB, or the location-based carbon intensity. And it's the same for all consumers. So on the other hand, the second method, the market-based attribution method, here, even after electricity is delivered into the grid, the sources can be segregated. And so the consumers can choose the source of electricity that is supplied to them. And how this works is via power purchase agreements, or PPAs. So consumers investing in renewables can have these PPAs, which enables or which attributes the generated green electricity solely to these consumers, and no one else can claim it. And they can use that to meet their electricity demand. And if they have any surplus electricity demand, even after the PPAs, that is met from the residual grid mix, which is the total mix minus any electricity under PPA. And and consumers who do not have these power purchase agreements, they receive only the residual mix, which has any green electricity that is not under any PPA. So in this method, the green electricity is first attributed to consumers with PPAs, and any remaining green electricity is then attributed to the grid, and which the consumers without PPAs receive. So let's take the same example and assume now that the data center on the right has a contract or has a PPA with the wind energy supplier or wind electricity supplier. And so what it means is, so it has a PPA and it buys all electricity to meet its total demand. So what it means is the data center can now claim that it only consumes wind electricity, which is green. And so all other consumers in the grid, so for example, the house which do not have a PPA, will receive the residual mix, which in this case is just coal. Note that even though, Yeah, even though physically the grid is delivering a mix of both wind and coal, um, the market-based method enables the data center to claim that it only receives wind electricity. So to calculate the carbon intensity for a consumer in the market-based method, first we have to find the residual grid mix. So in this case, I've assumed that all the wind is under PPA. So we remove that and get coal, which is the residual grid mix. And so the carbon intensity of the residual grid mix is just a weighted average of the carbon emitted by all the sources in this residual grid mix. And in this case, it's just 1,000, I mean, because it's just coal. And once we get that, then we can obtain the market-based carbon intensity for a particular consumer using this formula, where F is the fraction of electricity demand for that consumer that is met via PPA, and CIPPA is the carbon intensity of any electricity under PPA. So typically, electricity sources like solar and wind are under PPA, and so the CIPPA is usually zero, since we are talking about operational emissions here. So this term vanishes, and so this is the market-based carbon intensity for a consumer. And as you can see, it's different for different consumers because it depends on this fraction of electricity demand made by PPA. So for any consumer that do not have PPS, this F is zero. And so their market-based carbon intensity is essentially the residual carbon intensity. So in this paper, we have analyzed only consumers without PPS. So when I'll be referring to a market-based carbon intensity is essentially CIRES or the residual CI. So these two attribution methods give these two estimates, CILB and CIRES, and they are like very different from each other. So we show the temporal difference between these two CI with this plot. And also notice that CIRES is a little higher than CILB. That's because CILB considers the total grid mix, but CIRES considers the residual grid mix where some of the electricity is removed. So the residual grid mix is usually browner, and hence CIRES is usually higher. And this brings us to the problem that's there today. So currently, there is no standardized method of attribution. So as was also hinted in today's keynote talk. And also the residual mix information is not available in real time. So what happens is carbon intensity services, they usually provide only the location-based carbon intensity since CIRES is unknown. And all the consumers use the CILB to measure and optimize their reductions, including consumers without PPS. But at the same time, consumers with PPS have already claimed some of this green electricity. And so consumers without PPS should ideally use CIRES. And since they use CILB, and which can be significantly different from CIRES, there is a discrepancy in the carbon reduction numbers reported by consumers without PPS. And we highlight this in our paper. So specifically, the contributions are these. We highlight these discrepancies in carbon emissions, where consumers without PPS optimize using CILB versus if they would have taken the same optimization decisions, but evaluated using CIRES. And we do this across three popular carbon-aware optimization techniques: spatial load balancing, temporal load balancing, and carbon-aware auto-scaling. We also then assume the hypothetical scenario, let's say CIRES or residual carbon intensity is now available in real time, which is not the case now, but we assume that let's say it's available. Then we show that the optimization decisions are much different than what it is today. And we analyze the carbon reductions for consumers without PPS in that case, like if they use CIRES for both optimizing and evaluating. So I'll go into all these contributions now. To show the carbon reduction discrepancies, we take the example of carbon scaler in California. So carbon scaler is a carbon-aware auto-scaling technique that scales up resources during periods of low carbon and then scales them down during periods of high carbon. And so carbon scaler uses a third-party carbon intensity service that provides only the location-based carbon intensity and doesn't consider PPS. So it follows this red signal, scales up resources as shown here on the left, and then yields around 35% carbon reductions. But now, for consumers without PPS, I mean, they should ideally use CIRES. and assume, like if we assume that all the solar and wind, which are typically under PPA, let's assume that all of it is under PPA now. So the CIS is actually the blue curve, which is very much different from this red one. And so scaling up the resources at the same hours of the day would yield only 3% carbon reduction. So this is a 32.3% discrepancy if like in the carbon reductions. So in reality, the discrepancy percent may be a little bit less or maybe much less because not all solar and wind are under PPA and some are part of the grid. But in this paper, we analyze the worst case situation to show an upper bound of like how much discrepancy is possible. So our analysis for carbon aware auto scaling across 104 regions showed around 11.9% discrepancy on average and a maximum discrepancy of 55.1% in a region. Interestingly, in some regions, emissions may also increase when evaluated using CIRES. And this is not due to any fault of the optimization algorithm. It's just because when while optimizing, it didn't consider any PPS. But now we are evaluating using CIRES and considering PPS, so the emissions may increase. Next, we assume that this CIRES information is now available in real time, which is a hypothetical scenario now, but let's assume that's available. And we calculate CIRES, assuming that all solar and wind are under PPA to show the worst case again. And then we show that the optimization decisions are much different. So we take the example of spatial load balancing. And let's take two regions, California and New England, and look at the plot on the left, which shows, which shows CILB of these two regions. So the blue one is CILB of California. And since it has a lot more solar and wind than New England, so CILB of California is much lower, especially during the day. But if we assume that all solar and wind are under PPA, the residual mix of California is actually browner than New England. And so its CIRES is higher. So if we take the example of spatial load balancing, and if we follow CILB, we would actually shift our workloads to California during the day. But if we follow CIRES, we would shift our workloads to New England. And we find this type of differences in different optimizations, like other optimizations as well. You can find more details in our paper. And so now that we have assumed that CIRES information is available in real time, we analyze and quantify how much carbon reduction would consumers without PPS get if they used CIRES to optimize as well as evaluate their carbon reductions. We again go back to the example of carbon aware auto scaling in California. So on the left, we see the carbon intensity if no solar and wind is under contract. But as more and more solar and wind comes under PPA, we see that the residual carbon intensity increases. And more importantly, the temporal variations in carbon intensity decrease with this increasing PPA percentage. And so there's much less scope for carbon reduction for consumers without PPS if they consider this CIRES, and which is also reflected on this table in the right. So if no solar and wind are under PPA, carbon aware auto scaling would yield 35.7% carbon reductions. But in the worst case, if all the solar and wind are claimed by others, so then for consumers without PPS, carbon aware auto scaling would only yield 7.5% carbon reductions. So that is like 28.2% lower carbon reductions. And we find this consistent across the regions as well as across the other carbon aware optimizations like spatial and temporal load balancing. And in some regions, for example, in Germany here, in the worst case, it may be so that carbon aware optimizations may yield negligible carbon reductions. Again, like in reality, we do not know how much of this energy is like under PPA, how much of this electricity is under PPA. So we show the whole range of numbers, like if nothing is under PPA to if everything is under PPA. So to sum up, currently there is no standardized method of attribution, and also there's no information about the residual grid mix in real time. And this causes a discrepancy in carbon emission reductions. We show that it's up to 58.1% in our analysis. We also show that had this residual mix been present in real time, and if we could calculate CIRES, then the carbon reductions for consumers without PPS would be up to 28.2% lower than it is today. I would take this opportunity to call for a standardized method of attribution, as well as information about the residual mix and PPS like made available publicly in real time. And while that information is still not available, so as future work, we would like to analyze consumers who meet partial of their demand using PPS and then meet the remaining demand with the residual mix. So yeah, with that, I would like to conclude. Thank you.
So do you actually have residual mix data, and where did you get it, and did you use it for these studies, or did you imagine it?
Yeah, so for this analysis, we didn't have actual residual mix data. What we did is we assumed, so for the discrepancy analysis, we assumed that all the solar and wind are under PPS. So we just removed solar and wind to get the residual mix. Regarding actual data,
So it was made up.
Yeah, so that's why we said that this is the worst case analysis. Regarding actual data, so actual residual mix data is available for certain regions, for example, Europe. So there are bodies like AIB, which have this residual mix data, but they're usually lagging behind by years. So currently, I think 2022 residual mix data is available, but that too in annual granularity. So we don't have that, like publicly at least.
So I think that this work, I appreciate the rigor of what you guys are doing and so on. I think the conclusions are dangerous. And they're problematic. Let me just explain why. I think if you remove the residual mix and you use this as a basis for computing carbon emissions, basically you're going to destroy the power grids, right? Because there's no connection today between the generation of this carbon-free energy, right? And the only incentive to do that, right, is this shifting, incentive for low carbon. And if you remove that shifting incentive, right, what you're going to produce is a situation where the grids can no longer balance. So I'm really worried about this kind of
Right. I mean, you're right that removing to the low carbon times or periods is actually a good thing. And like if everyone follows the location-based method, let's say, and then does that regardless of the PPS, and that would actually work. This is just showing that if two methods are used concurrently, there may be some discrepancies in the carbon reductions, and there may be some overestimations of this carbon reductions.
Yeah, thank you for the very interesting study. So my question maybe is not directly related to the particular content, but maybe it is carbon intensity estimate in general. Today's grid, maybe there's still very little amount of storage in the grid, but many states like California has aimed to set up target to, let's say, install a sufficient storage system in the grid so that they can accommodate 30% of the peak demand, for instance. So my question is that once all these large-scale storage systems get installed into the grid, then how should we understand the carbon intensity at a particular point where the electricity can come from those stored in the storage system, which can be generated at some time ago, right?
Right. I mean, in that case, measuring carbon intensity would be more complex. So one way can be like, let's say there's a grid-wide storage. So when we are actually charging, what is the carbon intensity then, and use that when we are discharging, not so while discharging, it may not be totally zero, but it's actually the carbon intensity that was during charging. So, and then it can, we can measure carbon intensity in that way.
So in some sense, the storage will flatten out the carbon intensity discrepancy. Is that the understanding?
So for the discrepancy, I am not sure. I have to think about it. But let's say, okay, there's storage and everything, but there are two consumers and one consumer doesn't know about the PPAs of other consumer. So they would think that the grid mix consists of something, but the other consumer has already claimed some of the part. So then the discrepancy may still be there, but it would need more analysis, like if we include storage.
Thank you.
So here, so very interesting talk. So I think currently the companies are required to report both the location-based and market-based. So to me, it sounds like the market-based is more of a game, right? So because of physically we already generate this much carbon, and then some companies their carbon market-based carbon is low, then the remaining other players will have a higher market-based carbon, but it's physically still the same amount of carbon. We're just like redistributing from the paper, right?
Yeah, so I mean, as you said, companies are like, it's called dual reporting and they can report either. But the greenhouse gas protocol also mentions that they can use either, like the location based of they need to report, but they can use either to like account for their emissions. So basically the same, but if two companies use different methods, there is essentially some amount of double counting involved. So if everyone uses location based, or if everyone uses market based, everything is consistent. There's nothing to worry about. But if someone uses location based and someone uses market based, then there is some amount of double counting in the green electricity. And that may cause a little bit overestimation.
For their PR.
Yeah, we can talk.
Yeah, hey, thanks for the talk. That was great. I was just wondering, so are you considering anything, any changes or like differences in location, like within a grid, like within California? Or are you just taking like an average of the whole thing?
In this analysis, we just took like CAISO. So it's California, like the location based is for
All of
CAISO. Yeah,
CAISO.
what is provided by electricity maps. So
Okay.
the carbon intensity for California.
Okay, so do you think that for either of these approaches that like congestion like within a grid would matter, like something like locational marginal emissions?
It may matter. I mean, if we go into PPAs, there are a lot of types of PPAs, and then this congestion comes, like there are some PPAs called physical PPAs, which they ensure that at least the electricity is delivered to the consumers. I mean, it's a mix, but but then there are like financial PPAs and also that have no guarantee of this physical delivery. And then congestion and all those things would come, like, yeah, but we didn't go into such like the complex details in this analysis.
Gotcha, thanks.
Yeah, I think my question is related. So is there a way of putting this entire framework with OPF like formulation so that you can ensure that the deliverables can be made? Because there was a speaker earlier yesterday who talked about a lot of.
I mean, yeah, it can be. It's just that grid operators, they publish all the electricity that is generated by all the sources. And then these PPAs are usually maintained by renewable utility suppliers and the consumers. And there's no public database about this PPAs. Like, at least there are commercial databases, but I don't know if there's any public level. But
No, let me clarify. So what I want to say is about the PPAs and all that, there should be sufficient amount of solar in the system to deliver it, and it should be possible to deliver the solar to those loads, right? So is there a way you can ensure that in the optimization? That's what I meant. Even let's say as an academic exercise, can it be done? So when you talk of shifting, you also have that. I think someone already mentioned that when you optimize it, you can say that.
Can't be delivered loads. That's the whole point. The VPAs correspond to power that has a distribution that cannot be matched with the loads. That's the whole point.
Let me get back to that.
I think you can tell this one.
Yeah, like PPAs, there are again like several time granularities where they are matched. Like the most prevalent one today is annual matching of PPAs. So it says that annually the amount you consume should be equal to the amount produced by PPAs. So you can use solar PPAs for night. I mean, but then there are more granular, like 24/7 matching approaches that are currently like introduced today, but it's not as prevalent. So it's called like you match every hour of PP generation with every hour of load. And maybe in that case with OPF, like I have to think about it. I don't know the answer. Right?
No, because we're talking about shifting as well based on it, right? So that's my question.
Yes, time for last question.
Thank you for the presentation. I think it's important to understand the difference between the physical and the theoretical, like carbon emissions. But I also think it's critical to do any optimization with it And I have an example for that. In Europe, we have Iceland, and there's no electric grid from Iceland to the mainland. Though Iceland is taking part in the electric market, so Iceland is 100% renewable energy. So they sell their energy to the European companies in these PPAs. And in the end, Iceland, in your measure, would have a 100% coal, because it basically has no renewable energies. Then you would optimize in your model, and you would basically turn down plants in Iceland, because you say in Iceland it does not make sense to use energy. But in fact, it's very important to make a lot of plants and
Right, and
power systems in Iceland, because there is energy for free.
You are right in that sense, and also like what Professor Sheehan also mentioned. So what I think it's an open question. How do you incorporate both market-based locations, like take into PPAs, and then like you have to, when you are talking about optimizations, you have to optimize to low carbon periods or times. But this analysis is just to make people aware that, okay, this can also happen. And also whatever numbers that are being reported, they may be a little bit overestimated as well. But like there is an open question, like what we actually need to do so that there is no discrepancy, but we are still optimizing based on like what's intuitive. Like the intuitive thing is going to low carbon regions or periods.
Awareness, yes, but optimization.
Yeah, I mean, so that's like, we can think about how to do both, I guess.
Okay, thank you, Bob. That's all questions.
Okay.